Good morning, everybody. Welcome to AP Stats for Tuesday, March 31st. Today, we're going to do a quick review of the two-sample means testing protocol. All right. So, best to learn from an example. Here is the example we're going to begin with. We think that we're better than Derby in every way, right? Of course we do. So that would include the SAT math score. Well, let's see if data supports our hypothesis that we truly are better than they are. We take a simple random sample of 10 Derby students and 20 Shelton students. It's just what we have available to us, no problem, no issue, because there's also no strong skewness or outliers in the data. Here's what we find, and I'm going to create a grid while I review this with you. We have Shelton, we have Derby. I told you that there were how many students each? I said we had 20 in Shelton and 10 in Derby. The mean math SAT score we find in the Shelton sample is 540 with a standard deviation of 60 points. So I'm going to put that information right here, 540 with a standard deviation of 60. In Derby, the average SAT score is 525 with a standard deviation of 40. So they did have a lower SAT average in our sample. They also had a slightly smaller standard deviation, so their data was more consistent. Is this information going to support our claim that we're really better than they are? Well, we're going to test that philosophy at the 5% alpha level. What do I need to do? Well, I already wrote down the information about my sample, so now I have to verify my conditions, which are SRS, or some variety of random, the 10% rule, and the normality clause, normally distributed, or is our sample size at least 30, or is there no strong skew or outlier in the data? I told you the story that began with, we take a simple random sample of. Well, that's the given for our randomization. That was given to you in the prompt. And we get to move on to the 10% rule. Is the population of Shelton SAT test takers at least 200 people? Well, obviously, you guys know that there's more than 200 people in Shelton who could take the SAT. There's probably closer to, at any given year, about 700. So yes. And in Derby, is the population of Derby's SAT test takers at least 100? Derby is a smaller district than Shelton, but I think it's safe to say that there's at least 100 juniors and seniors combined in the Derby High School. So, yeah. Now, is the population normally distributed? Well, I didn't tell you it was, so you can't assume that. So that's a no. Is our sample size at least 30? Clearly it's not. We have 20 on one and 10 on the other. And to be honest, even if we had one sample size that was at least 30 and the other was not, we still could not move forward. They both had to be at least 30 for that part of the condition. So that's another no. However, what did I say when I told you about the sample size? I said there was no significant skew noted in the data. There is no skew. No significant skew. Now that's what's going to be our saving grace here, because that helps us normalize the sampling distribution and allows us to move forward with our problem. Got it? Good. All right. Now, I said I was pretty sure that Shelton was better than Derby. So what is my hypothesis here? I have a null and an alternate, and I think that Shelton's better than Derby. I wrote Shelton data first. So we talk about the mean difference. Now, if I want to talk about the mean difference, maybe I could even be more specific and say what that difference is showing me. So I'm going to say as a subscript, S minus D. The difference, Shelton minus Derby. If Shelton scores better than Derby on the SAT, what kind of difference would you see? Well, if Shelton has higher scores and Derby has lower scores, a higher score minus a lower score is a positive score. So greater than 0. Hey, where do I want to put that greater than 0? That's an alternate hypothesis. So my null is less than or equal to 0. If you just wanted to say equal to 0, that's fine, but less than or equal to is also perfectly acceptable, either which one. All right, I said we're going to test at an alpha of 5%. So what do we need to do? Well, I have to find, just like I did for the one sample t-test, our t-score for where we stand. I'm going to write the basic equation here, and then I'm going to erase it and fill it in with the actual values. Here's how you find the t-score in a two-sample mean difference test. The t-score we're looking for, the t-score for the difference, is equal to x bar sub 1 minus x bar sub 2 in parentheses minus mu sub 1 minus mu sub 2. This is the numerator. Now I'm going to pause for a second. Whenever we're using the number 0 in our statements, mu sub 1 minus mu sub 2 is 0. If I expected a difference of, let's say, more than 10 points, say I was very specific, I said, I think we're better than them, and I think we're better than them by at least 10 points, then that number is going to be 10, because these numbers are going to be 10. It's whatever this number is. If I expect the difference to be more than blank, that's what goes there. Whenever we're doing these tests where we're assuming a 0 for the null, the whole mu part of that numerator is 0. It's not necessary to worry about. But that's not always going to be the case. Sometimes there will be a number that pops in there. The denominator is the square root of the standard deviation of the first squared over its sample size plus the standard deviation of the second squared over its sample size. All right? Write down that equation. It's going to be important. Obviously, we have to use it. We have to understand it. It's got to be something that you commit to memory. Now, I'm going to erase it and put the numbers that will fill in for this particular prompt. So, in this prompt, mu sub 1 is 540, mu sub 2 is 525, not mu, I'm sorry, x bar sub 1, x bar sub 2. Don't let me screw you up. The mu sub 1, mu sub 2 is just going to be 0, so I'm looking for a 0 difference. Obviously, you don't have to write that down. I'm just placeholding it. 60 squared over the sample size of 20 plus 40 squared over the sample size of 10. That's my denominator. Okay, I trust that you can do this arithmetic. We're going to get a t-score for the difference of 0.8135. Just like before, I also still want a sketch. The sketch helps guide you, so please make one. Here's a small sketch. Zeros in the middle. 0.8135 is a little bit to its right. The alternate symbol said greater than, so I am shading to the right. So I have to find the area to the right, and I know how to do that, right? Just like with our one sample means test, we're going to use our TCDF function. So TCDF from a lower boundary of 0.8135 to an infinite upper bound with how many degrees of freedom? Remember our conservative estimate for degrees of freedom. We had two different sample sizes. One was 20, one was 10. The more conservative estimate is the smaller of the two sample sizes, which is 10, minus 1. So that's 9 degrees of freedom. That will give me my p-value. It's not a two-tailed test. I'm not going to double it. I'm just going to find the area in that tail. It's 0.2185, which is more than my 5% alpha. What is your decision when your p-value is greater than alpha? Please get this right. It's the same thing each and every time. If your p-value is higher than your alpha level, you fail to reject the null. We cannot reject the null. So based on this data, we cannot reject the null that there's really no difference. So there's no difference between Shelton and Derby. Here's another way to say it. We do not have significant evidence. We do not have sufficient evidence that would allow us to reject the null and say that Shelton is better than Derby. Please remember, p-values larger than alpha are not significant. They are not sufficient. They are not strong evidence, because what it says is there's a pretty decent chance of finding the data you found if, in fact, there really is no significant difference between the two of them. All right? Even though in our sample we had Shelton at a higher score than Derby, it wasn't strong enough to suggest that Shelton is, in reality, better than Derby. What's one good reason for our lack of strength in the evidence? Very small sample sizes. Small sample sizes have great variability, and it lets us, it leads us not to actually have that much support from that data. If the sample sizes were much larger, it might have actually been good enough to prove a significant difference, but it wasn't because of the data that we had. All right. You guys have one problem for homework in your textbooks on page 657. It's problem number 44. I'll also attach a photo of the problem along with this video prompt, just in case you misplaced your book. All right. Tomorrow we're going to review that. So that means I want you to solve this problem and email me your solution. Please email it directly to me. If you have any questions as to how to do that, again, please contact me. Most of you, I think, are on board with how this is going to work. So good luck, and it's just a one question for homework. Do it now, submit it soon, before the next lesson posts, before I give you the answer. That's how I'm going to give you credit for homework. Thank you, and have a great day.